data types, and then the income is a numeric data type. So one way we can calculate the distance or similarity of nominal features. So we want to know how similar this customer is, but we have a few nominal features. We can use this function. It's very simple. It's really just P minus M divided by P, where P is the total number of nominal variables that we have. In our case, there are 2. So we have refund and marital status. There are 2 nominal variables. And then M is a number of matches. So in our case, we have no matches in the nominal variables, right? So we have refund. One is a yes, one is a no. So there's no match there. And then we have marital status. One is married, one is divorced. So there's no match there. So typically, for this calculation, the first method would have 2 minus 0 divided by 2. The second thing that we can do is convert nominal variables to binary variables. So we went through this when we were looking at ensembles, but you just create features out of the variables that exist within a particular feature. So for example, refund can be yes, you have a 1 for yes and a 0 for no, right? And then marital status, you create features, like you say, okay, I'm going to create a new feature called married, where if someone is married, we put a 1, and if they're not, we put a 0. And then you create another feature called divorce, where if someone is divorced, it's a 1, and if they're not divorced, or if they're anything else, it's a 0. And then there's another feature called single, where if they are single, it's a 1, and if it's anything else, it's a 0, and then income remains the same. Now, remember we looked at the distance calculation for numeric variables. Now that's what we'll use after we've converted our nominal features into, we've hot encoded them, we've converted them into numeric features. So then now you can go back to either the Manhattan's distance or the Euclidean distance to calculate the distance or how similar these customers are. The same thing applies to ordinal values. You can treat as nominal, which is what we looked at here, or you can treat as numeric, which we've already looked at as well. Okay, so we'll go into normalization. I alluded to it a bit when we were looking at the ensembles, but I'll just go through this again because it's also very important when we're looking at our clustering or any kind of algorithm that you're building anyway. Let's assume we have 2 features, edge, whose minimum is 0 and maximum, assume our data set the maximum edge someone can have is 120. And then income, the minimum is 0, and then the maximum someone earns is 2 million shillings. So if we do not scale our data, then the model might give more weight to the income because of the hugeness of the scale in income. And then the impact of edge in whatever it is that we're building might be dwarfed by the contribution of income. And I've said the difference in scale would allow the income to impact the distance function much more than edge. If we do not scale the data, we might find that our distance measure will only differentiate an individual by their income, and the impact of edge will be dwarfed by the contribution of income. So you usually want to normalize your data and put these 2 features or whatever numerics that you have into the same scale from 0 to 1. So you find that Python and R as well, and I'm sure other programming languages that people use, have functions that can help you scale your data easily. Another importance, I'll go into another importance of normalization, but looking at text, and hopefully someone might take you through text mining or NLP. But then you find that in text, this is an example. You find that in text, when you're going to analyze text or do anything with text, and sometimes you even do prediction using text data, you have to transform your data first from text, that's the unstructured bit, into something that's structured, using what we call bag of words. So what happens is if you have a text, say, I love music, the word I love music will be split, and then features will be created from these words. So the word I will be counted, and so you count, the number of times I appears in a particular document, you count the number of times music and love appear in different documents. So this is what we are displaying here. So imagine we have 10 documents. 5 of them are about music, and the other 5 are about art. You find these are the different words that appear in all of the documents. So another issue that you'll have in text mining that you'll find out is sparsity, where you have so many features and then so many zeros appearing in those features. But anyway, this, you see that the first music document has the letter A appearing 13 times, and then the letter A appearing 18 times in the second music document, and it appears 20 times in the first art document. The word against does not appear in any of the music documents, so you have 0, and then it appears in 3 art documents, once, 2 times, and then once again. So this is typically what you'll have if you vectorize your data, if you're dealing with text. So you want to normalize your data because you want your data to be on the same scale. And when it comes to text, you don't want the longer documents to be very different or very far from the shorter ones, based on like the raw Euclidean distance that we've looked at. So you typically want to normalize your data in order for them to be on the same scale and for you to compare properly. So you can use 2 different kinds of normalizations. There's the L1 normalization, which is normalization by document length, where you get the word count divided by the total number of times, the total number of words in the particular document that you're looking at. So for example, for the word A, in the first music document it appears 13 times. So to normalize this, you can say 13 divided by the number of words that appear in the first music document, which could be 1,000 words. So you'll have normalized that particular letter. There's also L2 normalization, which is really normalization by Euclidean length, where you divide the word counts by the Euclidean length of the document vector. So this is really just an example of the importance of normalization in text and also generally in life. Imagine we build models to help us know which document is a music document and which one is an art document. And we use the raw Euclidean distance. We use L1 normalization and then L2 normalization. You find that for Euclidean, the raw Euclidean distance, we had 6 errors. So for the first part, the first music document, it was wrongly classified as an art document. The second music document was wrongly classified as an art document. There are a few correct ones, but when we count the number of errors in the 10 documents that we're looking at, there are 6 errors, which means that loosely means that we have a 40% accuracy, which isn't good. But when we look at the L1 and L2 normalization, the errors begin to reduce. So it's very, very important for us to normalize our data. In summary, we've looked at Manhattan distance, Euclidean distance. We've looked at the properties of distance. We've looked at how we can calculate distance for nominal and ordinal and numeric features. We've seen that we should convert nominal features can be converted to numeric for us to use the numeric calculation of distance. I would encourage you to read more about cosine similarity, but we've also seen the importance of normalization. So we'll now look at K-means algorithm. What K-means does is you have a centroid, which is like the center of the data, and then it builds clusters around that particular centroid, depending on how many centroids you've given it. So what happens is you select K points as the initial centroid. So this is where the domain knowledge comes in, where you have to know how many clusters do I want for this particular data set. So if you want 3 clusters, then you select K as 3. So you have 3 initial centroids. Then clusters will be built around those centroids, and then this process is repeated all over and again. It will calculate new centroids and then keep changing the clusters until the different centroids don't change anymore. So this is an example of the K-means clustering method. At this point, we have K is equal to 2. So we want 2 clusters in our data set. So we want the algorithm to create 2 clusters. So it picks 2 random points as our centroids. And then what it does is it creates clusters around these 2 centroids. So basically trying to minimize intra-distance within the cluster and maximizing inter-distance between the different clusters. Remember that concept. So it will assign each data point a cluster based on its closeness to the centroid, and then it will recalculate the centroid based on that, based on the two clusters that have been created, and then it will reassign different data points to the new centroids that have been created, and it will keep repeating this process until the different centroids stop changing. So then that's when it will stop, the algorithm will stop. So this is an example of a perfect clustering result where it's very clear that, you know, we have 3 different clusters, and these 3 different points, like you can just easily see from the way the points have been clustered that we have 3 clusters and they've been clustered correctly. This slide is really just an explanation of what I've just told you, where if we're looking for 3 clusters, we pick three random points are picked as centroids, and then different data points close to those different centroids are created as classes are created around those different centroids, and then it keeps repeating the process. Like you have different iterations until it can no longer change, or until the centroids no longer change, then there you have your perfect clustering result. Unfortunately, it's also possible to have a wrong clustering result where you have very, very meaningless results of your clusters. But this all really just depends on the centroids that you pick. So even with the k-means or with clustering, it's important for us to tune our algorithm, and there are different ways that you can tune them by maybe performing the analysis multiple times just to make sure that maybe, and also changing your random seeds as well for your data. You could use hierarchical clustering, like I mentioned earlier on, to help you determine how many centroids you should use for your k-means. And then you can select more k initial centroids and then select among these initial centroids as well. Another thing you can do is use the sum of squared errors to help you determine if a cluster is good enough or not. So you find that majority of the time we don't know, especially with this unsupervised learning where you can't calculate an accuracy, you can't calculate a precision, we tend to get confused and we don't know which cluster is doing well. We don't know when to stop. Sometimes you can use it's good for you to use the sum of squared errors to help you determine if your particular clustering, especially if you've built so many to compare, which one that you should use. But you should be careful because, of course, the higher the k, the lower the SSE. But then you also have to strike a balance between the number of k's that you want to have in your analysis. So we'll look at the code right now for the clustering. So for this particular algorithm, I picked a data set that I find quite interesting. It's actually a data set, it's structured, but it was created out of unstructured data. And it's a data set of about 85 essays that were written by 3 authors called Alexander Hamilton, James Madison, and John Ray. And a pseudonym called Publius, because they feared to be persecuted. These were writers in the US back in the day. So these are 85 essays, but then 73 of these essays, we know who of the 3 wrote them, but we don't know who wrote the other 12 or 11. I think they are 12. So what we can do is we can use clustering to help us determine which author wrote what essay, especially for the disputed essays that we have. So this data set has 85 observations and 72 features, and you'll see that most of the features are actually letters or words. They are words, that were used in the different essays. The idea is that you'll find that different authors have different ways of writing, and so you'll find that some authors use certain words more than other authors, or they use certain